Now we move to carbon dioxide storage. In the previous lesson, you saw hydrogen, the most difficult fluid to store. Carbon dioxide is different. It is more manageable, but it is not passive. This is where many errors begin. Hydrogen is clearly unstable. Carbon dioxide appears stable. That appearance creates a dangerous assumption that carbon dioxide is inherently safe. It is not. Carbon dioxide still moves. It builds pressure. It reacts with the rock and with materials in the system. This leads to a key rule. You cannot increase storage without controlling pressure. Improving injectivity must never compromise containment. So the objective is clear. Increase injectivity. Increase storage capacity. But maintain containment at all times. Final idea. Carbon dioxide can be controlled, but only if the system is controlled. Now let's define the real problem in carbon dioxide storage. Injection is not limited by one factor. It is controlled by two constraints at the same time: injectivity and pressure. If injectivity is low, the reservoir cannot accept carbon dioxide at the required rate. In many cases, the limitation starts near the wellbore. Damage in that region restricts flow before carbon dioxide even enters the formation. At the same time, pressure continues to build during injection. As pressure increases, the available operating window becomes smaller. This leads to an important consequence. You cannot increase storage simply by pushing harder. You will reach pressure limits before you reach the full storage capacity. So the objective must be balanced. You need to increase injectivity, maximize storage volume, and maintain long-term containment. But the priority is clear. Containment always comes first. Any attempt to improve injectivity must not compromise it. The type of reservoir also matters. Saline aquifers offer large storage capacity, but they come with higher uncertainty. Depleted reservoirs are better understood, but they can still evolve over time. In both cases, rock quality alone is not enough. The success of storage depends primarily on the seal. Now consider how carbon dioxide behaves. It is more stable than hydrogen, but it is still mobile. It rises. It moves through the system, and it builds pressure. Some of it becomes trapped, but not all of it. This leads to the critical shift in thinking. Carbon dioxide does not stabilize on its own. It only appears stable until pressure begins to build. Final rule. You cannot increase storage without controlling pressure. Now let's look at why injectivity becomes limited. In most cases, the problem does not start deep in the reservoir. It begins near the wellbore. Damage in that region restricts flow immediately. Even if the reservoir is of good quality, carbon dioxide cannot enter efficiently. There is a second mechanism: mineral precipitation. Carbon dioxide reacts with water and dissolves minerals. But as fluids move away from the well, those minerals can reprecipitate. The result is important. You remove damage in one location, but create blockage further into the formation. There is also a system-specific effect: salt precipitation. Carbon dioxide displaces water. Some of that water evaporates into the gas phase, leaving salt behind. That salt crystallizes in the pore space. This creates self-induced damage. The more you inject, the more restriction you can create. Another mechanism is fines migration. Particles move through the system and block pore throats. Put together, these processes reduce injectivity during operation. The system degrades as you inject, not before. The response must be controlled. Start with near wellbore cleanup. Remove damage without altering the formation. If injectivity improves, stop. If needed, apply matrix acidizing. This interacts with the formation, so the reaction must remain controlled. Keep the treatment local. Control both radius and chemistry. Hydraulic fracturing is different. It changes the system completely by creating new flow paths. The risk is clear. If fractures extend to the caprock, containment can be lost. Final rule: improving injectivity always increases risk. You are working within a pressure-limited system. If you push too far, you reach the limit. Final principle: improve flow, but never at the cost of control. Now consider what happens when control is lost. Carbon dioxide does not only face injectivity limits, it also creates its own failure mechanisms. The first is salt precipitation. Carbon dioxide displaces water near the wellbore. As water is removed, salt is left behind. That salt crystallizes within the pore space. Over time, injectivity declines. The system begins to damage itself during injection. The second mechanism is geochemical change. Carbon dioxide reacts with the rock. Minerals dissolve and then reprecipitate elsewhere. This means the reservoir is not constant. It changes during storage, and not always in a predictable way. The third mechanism is material degradation. Carbon dioxide forms carbonic acid in the presence of water. This can attack steel over time. As a result, well integrity weakens, and leakage pathways may develop through the well itself. These effects do not occur separately. The system evolves while you operate it. Not before, but during injection. There is also a fundamental constraint. Injection always increases pressure. This cannot be avoided. If pressure rises beyond safe limits, the system begins to fail. The caprock can fracture. Fractures can extend beyond the reservoir, and new pathways for leakage are created. This leads to the most important point. Once a leakage pathway forms, it cannot be fully reversed. Control, therefore, depends on staying within limits. Injection rate must be controlled. Pressure must be monitored continuously. The fracture gradient must never be exceeded. Now connect this to injectivity. You may improve flow, but the system always has a limit. If you push beyond it, containment is lost. Final rule: pressure defines safety, not injectivity. Now move from system behavior to decisions. You are operating inside a pressure-limited system. Injectivity is declining. Consider a typical case: a saline aquifer with moderate permeability. Over time, injectivity starts to drop. The likely cause is salt precipitation near the wellbore. The system gradually damages itself during injection. The correct response is controlled and sequential. Start with near wellbore cleanup. Remove salts and fines without disturbing the formation. If additional treatment is needed, apply a limited acidizing stage. Dissolve the blockage, but keep the treatment local. At the same time, adjust the injection rate, stay within pressure limits, and monitor the system continuously. If this is done correctly, injectivity improves, containment is preserved, and the system remains stable. Now consider the failure case. The same system, but the response is aggressive. Injection rate is increased, and pressure is not controlled. As a result, pressure exceeds the fracture limit. A fracture propagates toward the caprock, and containment is compromised. Leakage pathways are created. This is not a performance issue. It is a system failure, and it is permanent. This leads to a simple decision framework. First, check if injectivity is truly limited. If not, do nothing. If it is, determine where the problem is. If it is near the wellbore, use cleanup or controlled acidizing. If permeability is insufficient, fracturing may be considered, but only if containment risk is low. Always include a pressure check. If pressure approaches the limit, reduce the injection rate immediately. Final rule: if containment is at risk, do not fracture. You are not selecting treatments. You are managing risk inside a pressure-limited system. Final principle: the correct decision is the one that preserves containment under pressure. Everything in this system depends on one condition: containment must hold. Start with the seal. The caprock has to remain intact under pressure. No fractures. No hidden weaknesses. If the seal fails, the system fails. Fracture control is the next condition. Any fracture must stay inside the reservoir. If it extends upward, containment is lost. The third condition is plume control. Carbon dioxide has to stay within the storage boundary, not where it wants to move, but where it is allowed to remain. If any one of these conditions is lost, the system does not partially fail. It fails completely. Compare this with hydrogen. Hydrogen is highly unstable. Carbon dioxide is more manageable, but only when it is controlled. They behave differently, but the governing rule is the same. Containment controls everything. Hydrogen moves faster and is harder to contain. Carbon dioxide moves more slowly. and part of it becomes trapped. But neither system is safe without control. This affects how you intervene. Hydrogen requires minimal action. Carbon dioxide allows controlled intervention. But in both cases, fracturing is highly restricted. So the principle is simple. It does not matter which fluid you are storing. The system is always limited by containment. You are not designing stimulation. You are protecting the seal. Everything else comes second. Final line. Containment is the system. Reduce everything to what matters. Carbon dioxide storage is governed by two variables: injectivity and containment. Both must be controlled at the same time. Most injectivity problems begin near the wellbore. Salt precipitation, mineral blockage, and formation damage gradually reduce flow. Stimulation can restore injectivity, but it must be applied in a controlled sequence. Start with cleanup. If needed, move to acidizing. Fracturing remains the last option. Each step increases risk. So it must be justified. Fracturing can increase capacity, but it also creates new pathways. If those pathways reach the caprock, containment is lost. Carbon dioxide also alters the system during operation. Salt precipitation and geochemical reactions continue to change the reservoir over time. This is not a static system. It evolves as you inject. Pressure is the defining constraint. If pressure approaches its limit, the injection rate must be reduced immediately. The rule is simple. Improving injectivity must never compromise containment. This leads to the correct mindset. Storage is not maximized by injecting faster. It is maximized by preserving containment. Final anchor. Store it correctly, or you will lose it. Now step back and look at the bigger picture. You have seen two storage systems. Hydrogen, which is difficult to control. Carbon dioxide, which is more manageable, but still limited. The key lesson is not about the fluid, or the method, or even the system itself. It is about how you think. Most engineers approach storage the same way they approach production. They increase the rate. They increase the volume. They push the reservoir. That may improve performance in the short term, but over time, it leads to loss of control, and eventually, loss of containment. A controlled engineer works differently. They do not push the system. They respect its limits. They diagnose before acting. They stop before the boundary is crossed. They protect the seal at all times. The difference is clear. Two engineers can work on the same system, using the same tools. One loses the reservoir. The other preserves it. The difference is not knowledge. It is discipline. Final principle. Success is not defined by how much you store. It is defined by whether it stays stored. Final line. Control the system, or the system controls the outcome. Hydrogen and carbon dioxide behave differently, but they follow the same rule. Containment governs everything. Hydrogen is clearly unstable. Carbon dioxide appears more stable. But both systems fail as soon as control is lost. Improving injectivity can enhance performance, but it also increases risk. And there is always a limit. Pressure defines that limit. If you cross it, the system does not degrade gradually. It fails completely. This leads to a simple principle. Success is not measured by how much you store. It is measured by whether it stays stored.